years ago, 2018, around March meeting time. I'll introduce that problem and also what we did, not superconductivity point of view, but I'm most interested with the electronic structures and the Van Hove singularities. So our original motivation for the problem is just that. So my title is the Van Hove singularities and the flat bands in this twisted graphene, or we can say simply twisted bilayer graphene, which is the popular word during the last 3 years, or even we have an acronym, just the TWISRONICS. So this is a very active field. Several leading groups are working both experimentally and theoretically to understand, to explain this simple system. Simply, I'm just showing here. Here we have a bilayer system of the graphene. So they are AA stacking on this one. If you just concentrate over the angle here, we have a perfect stacking at the beginning. Then there is a slight rotation around 1 degree. Then you see an extended periodicity appears on this Moore system. So I will show that reported experimental result as well. But even here from this simple, on this very simple system, on just a very simple rotation, actually a tiny rotation, you see the pattern formation with an extended period. Then what we can see, I'll just try to motivate you during this talk. So I'll skip this introductory slides. These are already introduced and well known within this community, I guess. But I'll just emphasize here, you see the picture of the three-dimensional picture of the graphite system. It's either you can see like a coal or the pencil and so on. So this is a layered material. So on this talk, I will just confine 2 layers of this graphite. So it's not a single layer graphene, but it's 2 layers of the graphene, bilayer of the graphene, and I'll just going to look at these 2 layers. This can be AA stacking when the atoms are on top of each other, or AB stacking. So energetically, the energy difference is very small on the bilayer system. Both of them can be realizable. But for simplicity, I'll show the results for the AA stacking just to simplify the structures and so on. So, I mean, this is the part of the introductory slides. So the work of Gaiman and Novoselov end up with the Nobel Prize in a very short period. From 2004 to 2010, they end up with the Nobel Prize that shows the importance of this new field. But every year, actually, we have some variations and so on. So, but let me confine my talk in this limited time just to Moore and this twisted bilayer system. So our motivation to study this system, so we have this located graphene, okay. So as I showed, there might be some rotation, and the 5-6 years ago, the motivation was about the STM experiment, and STS experiment, and look at the energy spectrum, the Van Hove singularities, and so on. So our motivation is just to understand this origin of the Moore patterns. Since STM experiments, if you are a little bit familiar, the image you observed might be formed through the electronic effects as well as the morphological effects. So we want to answer, we start the problem just trying to answer this question. So what is the observed pattern? So how this is produced? and look at the reason of this. Is it electronic or the morphological and so on. At the end, we end up with a quite surprising result, even similar to the this superconductivity I will mention in a minute. Okay, so this was our starting point. So let me continue again. So as I said, this is the bilayer graphene system. It can be, so here I'm just showing the AB stack one. So one of the carbon atoms just sitting at the center of the hexagonal one, while the other carbon atom is just sitting on the carbon atom. AA stacking is also possible. In that case, all layers, two layers are aligned perfectly on top of each other. So when you look at the SDM, you can, it is possible to achieve the atomic resolution over this graphite system. Let me jump to this rotation. So just to show the effect, so I pick a very simple lattice, Sukar lattice. So it's like a condensed matter course textbook example to describe these two-dimensional things. So if I put the bilayer, two of them on top of each other, and if I rotate, even I mean on this picture, you realize that this super periodicity. So this here with the Sukar lattice, this is the lattice constant, a small periodicity, but depending on this angle, rotation angle, you might have the new pattern formation and a new periodicity just appearing here. So this is what we expect on such a regular two-dimensional planes. Okay, so if we specifically look at the graphene system, so here I'm just showing. I start with the AB stacking. So we have two layers, blue and the pink one. So originally there is no rotation, 0 degrees there. Just like a simulation, just look at the 5 degrees, you see the formation of these larger hexagons with this amount of the periodicity. So when you go 10 degrees, you see a more confined picture. The periodicity is smaller compared to this 5-degree rotation. Then even if you can go further, 15 degrees, so on, so on. Since I mean, this will go till to the 30 degrees, after 30 degrees, this will repeat itself. And actually this is well known, and this periodicity predicted just using these geometrical factors, and that's published almost 30 years ago. Okay. Yes, now on this figure, I'm just specifically showing this periodicity that we can represent by just simple geometrical factors. D is the periodicity in the original lattice, and theta is the rotation angle, D is the periodicity in the Moore system. Here, I'm just showing one example from the Oğuz Gülseren group, Istanbul Technical University. Just using a very simple SDM system, they were able to get the atomic resolution both on HOPG and also this rotated graphene system, and you see quite nicely this new periodicities can be identified and so on. Now let me go a little bit quickly. So I mean, as I said, our motivation to understand this SDM picture to describe its contribution coming from electronic effects as well as the morphological effects and so on. So with a quite surprise, what we observed first. Okay, before going there. So let me introduce this motivation as well. So this is the picture I showed at the beginning. So with a very small rotation, now I'm just showing a larger area the rotation around 1 degrees, you see this new pattern formation, the periodicity even much larger now at the small angle. Then with a quite surprise, the unconventional superconductivity was observed at this magic angle on this graphene superlattice. So this is the just the abstract of the paper published by this Harvard group, and this is their data, just showing the superconducting transition. You see there are two different rotational angle, and the resistance just dropped at the quite low temperature, around 1 Kelvin, and on this one even lower than that. But there's a definitely this superconductor transition observed. Here, to explain this, this is not the full mechanism there, but they provide a DFT calculation, a band, actual band structure calculation. What's shown at this 1 degree rotation, there is a flat band just coincide at the Fermi level, and this might be this quite strange electronic structure. Just already shows the evidence for this unconventional superconductivity. After this report, there are several studies still working on this from both experiment and the theoretical point of view. So here today on my talk, as I said, motivated from this STM experiments, we try to calculate and understand its both charge density, that's quite critical for the STM experiments, and also the electronic structure. So in order to do this, what we start, just the AA stacking lattice, then we fix the origin at the center of one of the hexagons, then rotate, we introduce this rotation with a quite simple strategy. So we rotate one of the layers clockwise, then the other layer counterclockwise with the same angle. So if I have a one lattice vector, so this way I can guarantee to get so if I just follow this, so this angle is same, that will set a new unit cell, and that will give me the unit cell of this Morse system. So just to open such an approach, we construct the lattices and do the DFT calculation for get the charge densities to understand, first of all, for the STM experiments. So here I'm not talking about the superconductivity, but even from the electron structure that I will show, that will show the peculiarities that might be quite important. So the first thing, what you observe, even though your atomic resolution is quite important. So I'm just showing two center here, and the charge densities are different from each other. So on this one, we have an empty spot while we have a center there that you can easily miss from the STM experiments. So I'm just showing here a little bit in detail. So within the same thing, actually the actual real periodicity, not from this center to that one, but actually you have to use that oblique lattice. So you have to differentiate these local configurations that might lead to the some misanalysis of the periodicity from the STM experiment. So this is one important result. We first realized, okay, I'm just trying to go. So let me go. So one has to be careful to identify local geometry. So let me go over the electronic structure. Yes, we have one over singularities, and that one over singularity actually depends on the rotation angle that shifts in the energy. Then for the smaller with the increasing angle, the position is also shift to the things. Let me conclude in the just using 2 more minutes with the electronic structure. Here I'm just showing the band structure for this 2 different situations. Okay, so if you look at both of the cases, so for example, let's start from the one on the left. You see we have a one hour singularity. So in the dense of states, that means there should be some saddle point in the band structure. Actually, yes, this happens because of this band just shows flat region over there. Then similarly, this is the other way we can think. One is the rotation along the zigzag, the other is the armchair one. So on this one, this happens from point near the M point. This arises from the point around the K point. Then you have to look at these tiny details of the rotation angle, how the Brilliant zone of the larger Moray unit cell shifts, and that's connection to the this one. But what is peculiar here, actually, we do have flat bands on several places in the electron structure, even in the lower energies. So with the magic angle, so this is going to be my speculation, my final speculation, these flat bands are just coincides with the Fermi level. These shifts, and they appears at the around the Fermi level as it was shown on this Harvard's paper. But apart from that, actually we do have these flat bands of different positions, and that might lead to these singularities and the peaks in the dense dose states. And just applying the voltage or just playing with this angle, actually you can shift up and down these flat bands, and you can tune the transport properties accordingly. So with that, I think I'm at the end of my time. Let me thank to all of your attention. I'll leave you with these 2 main conclusions from our calculation regarding to the STM experiments. Thank you.
Because I have seen this work, there was a lot of noise about twisting graphene and having this superconductivity phenomenon, which is, I guess, measured with resistance. And it's just a difference of one Kelvin in the zero resistance, if I recall correctly. Do you think it is usable in any way? Do you think it's something that can be exploited, that can give also information on the mechanism of?
As the previous talk says, there is no defect, no vacancy, so there is no magnetism or these unusual states and so on. This is a very perfect system. Then you just rotate, and as a result of this rotation, you introduce this unusual behavior. So from fundamental physics point of view, this is very, very interesting. On such a simple, just a sp2 type of the chemical bonds, and you end up with such a flat bands without any defect, any impurity, and so on. This is quite astonishing.
Okay, thank you very much. And,
Thank you.